Good morning again on the West Coast. Good afternoon, I think already on the East Coast, and good evening for the attendees joining us from Europe or Asia. Today is our last training session on Xendee, and today we are focusing on financing bankability. And this is our last session, and we have probably some time to also go through some questions from the audience as we did yesterday. So we can easily do this. And I'm here today again with Rita. She will again walk you through the tool, and I will start with some background information on financing. And also Ray is here. Ray is one of our senior engineers. He's working on the technology in the background and also with clients. So he will also help you or us if you have more questions to get through this session. Okay, next slide, please, Rita. So as I said, the first thing is a little bit background on financial methodologies, key financial matrices in Xendee, and then this live walk for Xendee. Again, I'm not sure if you joined session 1 and session 2 on the training, but because of the number of people interested in this training, we decided to do this as a walkthrough. And after the Xendee University Week next week, we'll send out the credentials, the password and usernames, so that you can have your 2 weeks training or trial license and use it. Rita will be here to support you also at that time, and other colleagues of mine at Xendee. So this is just, as I said, the last 2 times are designed to set the stage and hopefully you better understand Xendee. So next slide. So financial modeling in Xendee, and it's interesting because this topic is not really the most favorable topic of engineers doing projects. And we have observed this a couple of times that when our clients or we ourselves, when we do modeling and analysis with Xendee, a lot of people start focusing on very, very little details on the technology side, like changes in the efficiency. How will the efficiency change over time? Of course, these things change results, but financing and how you model the economics of a project tends to have a very, very large impact on the outcomes. And this is why we are focusing on this, because it will drive the results considerably. And you will see this also later on when Rita is walking through the model. So we have basically 2 sets of cost modeling. One is a levelized cost of electricity model, LCOE, which you see on the right-hand side. And then there's net present value calculations, which you see on the left-hand side, which are basically upfront cash purchases and loan purchases, but they always optimize the net present value. And they are characterized by a project lifetime, discount rate, and interest rate. In contrast, when we do a levelized cost of electricity calculation, which is also called amortized cost calculation, the costs are based on the technology lifetime, each individual technology lifetime, and an interest rate. There's no discounting. And I will talk about these differences a little bit more later on, but they really drive the differences here. And in Xendee, you can then combine amortized cost or levelized cost optimization and net present value optimization also with energy as a service and the charging as a service approach. So next slide, please, Rita. So you will see this also in the input sheet then a little bit when Rita is walking you through this. But the first thing is amortized costs, and it's actually overlooked a lot in the industry. And most engineers and modelers that we are seeing go into net present value. But amortized costs is a concept which actually comes from the utility industry, where you want to calculate the different levelized costs of power plants. So it's so basically what you're doing is you take all the costs and levelize them or put them over the lifetime of each individual technology. So there's no concept of a project length. It's more like a certain equipment lasts a certain period of time, and what you're generating in terms of energy over that lifetime needs to be considered for the capital costs. And the advantage of such an approach is that you can compare technologies with different lifetimes. And that's exactly what the utility industry is doing. You have gas turbines with a certain lifetime. You have renewable technologies with a certain lifetime. So you cannot just use a project length if you build a power plant. You actually want to normalize the costs over the energy output of its technology. And that's also what we're doing here. And this gives you a really powerful way of comparing different technologies on how attractive they are in a microgrid. And we have a lot of different technologies in a microgrid with different lifetimes. I mean, a PV system lasts 30 years. A generator maybe lasts 15 years or maybe 25 years if you do major maintenance, right? And all this will, of course, then impact the economic outcome. So one other thing on this is, as I already said, there's no project lifetime in amortized capital costs. There's we just use the lifetime of each individual technology, and we'll see this later on. So next slide, please. So amortized costs in Xendee. So this is a screenshot from the manual, for now, just forget about the charging as a service revenue at the bottom. We're just focusing on the OpEx and CapEx here. And as you can see, we have in this example, we have 3 technologies: PV, solar PV, inverter, and battery, and they have different lifetimes. And in this example, we assume that we have a 5-year lifetime for inverters, for batteries a 12-year, and for PV 20 years. So just for this example, right? And you see that over time, we always reinvest in these technologies. As you can see, this is an indefinite time horizon, because when the time comes, we replace the inverter, we replace the battery, or we replace the solar PV. And this keeps going and going. And this is why there's no concept of a project length, but at the same time, since we're normalizing to the energy output of each technology, we can, in a fair way, compare the different technologies. Next slide, Rita. So, I mean, just for documentation here, how we calculate the amortized costs. It's basically the annualized capital expenses, which is the capital cost multiplied with an annuity factor. And this is the interest rate. It's not the discount rate. It's the interest rate that you're assuming. And it's also built by the lifetime of each technology. So there's an annuity factor for each technology and not for the entire project. So that's a big difference to other financial methodologies. Next slide, Rita. So, oops. I think we have upfront cash purchase. So upfront cash purchase. So here we optimize the net present value. And the thing is, we're not taking out a loan. We assume that everything gets purchased upfront with your own cash, okay? And now, since this is a net present value calculation, we're also talking about discount rates and the project length. And the project length is now really the thing here, because what we have seen is a lot of modelers assume a certain project length just randomly. I mean, okay, let's say 20 years. Okay, 20 years is a reasonable project length, right? But the question now becomes, what if the technology has a very different lifetime than the project length? So let's say we have a PV system which lasts 30 years, and we have a backup generator which lasts, let's say, 5 years, okay? Then with a 20-year lifetime, you might discourage in a net present value calculation the PV system, because after 20 years, you're actually shutting down the project in your mind, in the modeling, which means you're throwing away 10 years of revenue stream from the PV system, which makes it less favorable than a technology which has a lifetime which is linked to the project length, or let's say 20 years, or it can be reinvested in 5, 10, 15, or 20 years, right? So this is why we have this difference between amortized costs and net present value approaches. But in this case, upfront cash purchases, as I said, discount rate comes in and we have a project length. So next slide, please. So this is how it looks like in Xendee. Again, we neglect the charging as a service revenue, CaaS revenue at the bottom is just an example here. Again, in the middle, we have the OpEx, and then on top, we have these different colored boxes for reinvestments. And then, of course, since this is an upfront cash payment, we have in year 0 all the investments. So you see that this is why we have this huge gray bar upfront capex in year 0, because this is when we do the reinvestment. The project length in this example is 25 years. And now let's talk a little bit about the maintenance costs, because as we know, we have different lifetimes for technologies, right? And sorry, I confused it. Not the maintenance cost. I meant let's talk about the reinvestment costs. The reinvestment costs, which are these different colored arrows here as a boxes. So every technology has a certain lifetime, and if the lifetime is smaller or less than the project length, then we have to reinvest or replace the technology in the project. And this is why we put some money away. This is the accrued approach here, which looks like we have very stable money. So we put stable amounts of money at the side, which are this greenish, bluish, yellow, and reddish bars for reinvestments. But then when the end of the project comes, we already know that we don't have to reinvest in certain technologies because we know the lifetime and we know the project length. So we have to put aside less money. And this is why these bars becoming smaller and smaller in an accrued upfront cash purchase, okay? And actually, I want to stop here and see if we have QAs. Because I just want to make sure that people are following here. Ray, maybe you want to read that question for everyone instead of typing it. So there's a question from Max. So maybe, Ray, you want to read the question, then say the answer.
Sure. So we have a question from Max. So his question is, for something like chargers or batteries, is there a way to roll out units in stages? That is, 10 charges in year 0 or an investment year, and another 5 in another year, and so on. So the short answer is yes. This can be done through multi-year modeling with amortized cost financing. So with amortized cost financing, you could specify actually the years where you could install technologies. So with that, you could specify like year 2, year 3, or year 4 that you could invest on these technologies. Depending on your project, you may need to also model like load growth to also drive investment on these technologies.
Yeah. And as I said in the beginning, we might have some time, and we can show you easily how this multi-year works, because yesterday was also a question regarding multi-year, okay? So, but I hope it's clear what I'm talking about here about upfront and the replacement costs. If not, just let us know in the Q&A. Rita, next slide, please. So this upfront cash purchase can also, of course, have, we can consider a different replacement strategy with upfront cash purchases, and it's called lump sum. So basically, we're not putting aside money every year. With lump sum, we just spend the money when the replacement is happening, okay? And this is what you're seeing here with on top in this yellow, orange, and bluish bars. So whenever the technology is up for replacement, we have to spend that money. So it's a discontinuous money spent. But there's one thing I want to point out here at the end of this project lifetime in year 25. And you tell me if this makes sense or no, but for me it doesn't. So we have this red bar, and we have for the battery replacement, and the yellow one for the inverter. So we know that we, in our mind or in the model, we say it's a 25-year project length. But then in year 24 and 25, we have to replace the technology, spend all the money just a year before we shut down the project, at least from an economic perspective. So that's a little bit of a challenge, and of course will impact your economics. And maybe and this is also an indication why you should think about a project length in a net present value calculation, because maybe you want to make the project 23 years to get better economics, or maybe you just use an amortized capital approach as described at the beginning to do the analysis. Okay, there are a couple of, there's another question now from Vince. Okay, Ray is answering this, so then Ray just keep answering it and I keep going. So Rita, next slide, please. So loan purchase, again, a net present value approach, but this time we decide that we either finance everything through a loan or a certain portion for a loan and have some upfront cash payments, right? And this makes it a little bit more complicated in terms of input data, because now we have a loan length, a project length, and then of course we need to specify how much we want to finance. In this case, it's 80% financed through the loan. But we could also let Xendee decide on an optimal investment rate here. Again, we have discount rates, and of course interest rates is coming back for the loan. Okay, so next slide, please, Rita. So loan purchase, again, how does this look like in terms of timing? So again, at the bottom, the charging as a service revenue, which we ignore. We also ignore the OpEx for now. This is in accrued replacement. This is why you see at the end of the project that these three colored bars are getting smaller and smaller, again, as already explained. But now let's focus on the loan. The loan is a 10-year loan, which this is why we have loan payments from year 1 to year 10 for the different technologies. But in this case, it's also a combination between loan term and upfront cash payment. And this is why we have also in year 0 a cash payment and then the loan terms. And again, of course, I mean, the portion that you're taking out for the loan and that you're funding yourself will again drive the financial situation and the technologies adopted. And I think you already get the idea why I was saying at the beginning, it's important to model all the details on the technology side, but sometimes we're getting carried away to focus too much on the technology and not enough on the financing, which maybe is sometimes a bigger driver for the results in adopted technologies and how we run technologies. So next slide, please. This is again loan purchase, but now with lump sum again. So we have a loan with 10 years, which goes from year 1 to 10. But now on top of this, we have the replacement cost with lump sum, which are these yellow bars or the bluish bars or orange bars, depending on the lifetime of the technology, right? So it looks already a little bit complicated, and depending on the lifetime and when the replacement happens, this can also impact your finances, of course, and the technology considered. Okay. Maybe Ray, you want to answer the question for Dick, for everyone, because I think that's maybe also important for the full audience here.
Sure. So the question is, wouldn't it be optimal to set your project length to, let's say, the longest expected CapEx lifetime? For example, 30 years driven by the PV. So that's possible, but not necessarily applicable in all projects. So for example, if there's a generator with a lifetime of 25 years, you're going to account for that huge replacement cost for that generator within the 30-year project. So it would disadvantage the generator because you're accounting for 2 generators instead of just compared to 1 for the PV. So again, it's possible that you could do that, but it may not be applicable in all projects.
Yeah. And I think I want to answer the question from Pablo about the salvage value. So Pablo is suggesting we could use a salvage calculation to get rid of this. And it's not in this diagram, but of course we have salvage and scrap value in the model. But my point here is there are a lot of different things that will influence it. And yes, Of course, salvage value can take care of this to some extent, but you need to model it, right? Yeah, decommissioning costs. Vince is asking if decommissioning costs, I mean, we have salvage value and scrap value in the model that can be considered, yeah. So decommissioning is probably a different term for either salvage or scrap value, or you can use one of these things to model your decommissioning, yeah. Okay. Okay, next slide, Rita. So now this is a little bit of a different view on how we calculate the loan purchase. I mean, remember we had the annuity factor in the amortized capital approach, but it was the technology lifetime. Now the annualized or the annuity factor at the bottom of the screen is the loan length, because we're taking out a loan. So the annuity factor is based on the loan. And then with this annuity factor and the percentage of how much is financed, we can calculate the annualized capital costs in this calculation. And then, of course, this gets discounted later on, depending on the reinvestment and everything. Okay, next slide, please. Okay, so now, before we jump into the tool, just for the records, so that everyone sees how we calculate this, and we have also a lot of this stuff in the manual. And Rita, I think we also have engineering movies and support movies around financing, if I'm not mistaken, right?
Yeah, there's a few resources we have online.
Yeah, okay. So just so that we put this on the screen, how we calculate the net present value, it's just a standard calculation, which is basically the cash flow at each time, basically discounted to year zero where we do the investment, right? So basically this delta is basically the discount rate, and then you see 0, 1, 2, and so on, which are the discount, the years in which we have this cash flow, right? And the cash flow, of course, considers CapEx, which in this case is negative, because the negative net present value, we don't want to do this. OpEx savings are positive, revenue streams are positive, and incentives are positive. And this gets all summed up and discounted and then summed up, right? And as everyone probably knows, we go with a project which has the highest net present value. And if it's a negative net present value, then it's bad, because we have more outflow of cash than inflow into the system. Okay, so just to set the stage here. So next slide, please. So this is already how this looks like in Xendee. And I want to go through this a little bit, because sometimes, I mean, I get confused all the time by reading these lines. So this is why we want to go a little bit through this, right? And Rita will show this also live. So you see here in this dotted box, the net present value. The first thing you see is it goes from red to green. And green indicates this is the year where, I mean, of course, where the net present value turns positive. So when the project becomes positive and should be considered. But again, and this is probably not news to most people, but again, depending on your project length, you can have a very high net present value. Let's say your project length is 20 years, then your net present value is $22,862,000. But if your project length is only 10 years, then of course the net present value is only 3,947 in this case, right? So, and also just to make sure that we understand on how we calculate this, because we have different terminologies here. So let's calculate, and Rita, you please point this out with the mouse, that the net present value for year zero, which is very simple, because in this case, we have a CapEx and outflow of cash of minus 119,288. We get incentives of 51,460. If we add this up, the cash flow for this year is minus 67,928. There's no discount applied because it's year zero, so the net present value for this year is minus 67,928. Very simple, right? So let's go now to year one. In year one, we do the same thing, but a similar thing. So we have OpEx savings and replacements, 3,990 positive, add this to the total incentives of 32,095, and we get the net annual cash flow without any discounts of 36,085. We now discount the 36,085 to year 0, which gives us 34,367. And we add this number to the previous net present value of 6728, and this gives us a net present value of 33,561. So it's cumulative, the sum of all these discounted values, okay? So that's how we calculate this net present value, pretty standard, but I'm just telling you so that you can replicate this in the table when you go through this yourself. Okay, I think we can move on to the next slide. So now there's this terminology which we call cumulative costs, non-discounted and discounted. And that's probably not very standard, and this is why we have to explain it, but we need it later on to calculate the break-even point in the system, and this is why I want to point this out. So again, same exercise. For year 0, nothing is basically changing, right? But I'm not concerned about the last 2 lines, cumulative costs non-discounted and the cumulative costs discounted. So let's do year 1, and I need to think about this myself. So again, the net annual cash flow non-discounted is 36,085, which is just the sum of the 2 positive income values, 3,990 at the top and 32,095. So this is the cash flow in this year, non-discounted. So now we can, of course, discount this, but in this calculation for the cumulative cost, we're ignoring this, because in the cumulative cost non-discounted, we just add up basically the negative 67,928 with the 36,085, and this gives us the 31,843 non-discounted, right? And then the discounted one is just now the total number discounted. So the thing is, with net present value, you discount every term and then sum it up. Yeah, well, you discount every term and then you sum it up, and then the cumulative one, you sum it up and then you discount it. So this is how this is calculated. And there are some comments already about this. And the thing also with this financial methodologies, what we learned is there's no right or wrong, because there's a comment from Edward that the big issue with this is then how to determine the discount rate. And the thing is, we use this for the break-even calculation. For the break-even calculation, we need to use exactly this definition. So that's also a lesson that we had to learn the hard way. For different projects, you can settle on either using a net present value, LCOE, or you're focused on break even. But you need to make this determination early on. What's your important driver for this? And we report all these different things, and we can optimize for these things, but it's up to the user what is the important financial indicator on this, okay? Ray, since you're the expert on this, anything to add on this?
Yeah, sure. Regarding the discount rate, so that's really a challenging metric. Different projects or institutions document it differently. So ultimately, it really depends on the institution. Some of these have like financial departments that they would set out like a standard for all their projects. Or for specific projects, they would say this is the rate. For another projects, this is the rate. So there's no as you might have known, there's no straightforward answer to this. Ultimately, it's based on the market, as you mentioned, but it really depends on how you do the financials for your company.
Yeah, and actually, a main reason why we have this session and these slides is to make the audience and also our clients understand that there are different ways of doing it, because we have clients come and say, well, you're doing this the wrong way. And so we say, no, we're not doing this the wrong way, because you can do it this way or that way, right? And this is very important to realize in this analysis. And it actually becomes way more complicated if you think about multiple energy carriers, because think about what all this levelized costs of electricity mean if you suddenly have a microgrid with heating and you have natural gas involved, because it's somehow easy, let's say, if it's only electricity. But if you have multi-energy carrier microgrids, then everything gets bundled into energy and not electricity anymore. And we have seen projects where they wanted to understand what the cost for heating, the cost for electricity is. But in an integrated system like this is very difficult to determine. Okay, there are a lot of questions around this. Maybe Ray, you want to take them, and are you already typing? Okay, good. So next slide, Rita. So, and this is the last thing, which is maybe confusing people, but I have to point it out: the difference between payback period and break-even point or year. And there are, of course, textbook definitions around all this, right? For example, the payback period, the textbook definition is initial capex divided by the average annual savings. Well, we know that we have reinvestments with microgrid, so what to do about initial capex, right? Then average annual savings, maybe not a good thing, because there's volatility in the system, right? So this is why we had to adopt this a little bit in Xendee. And then the break-even year, which is a little bit more detailed, is actually a year where the cumulative non-discounted cash flow turns positive. And this is why I was explaining the non-cumulative cash flow at the beginning, why we are doing this. But basically saying the break-even years where your capex is the sum of the non-cumulative cash flows, right? And they're somehow related, actually, the break-even and the payback period. And I did the math actually on this, and we can show you this if you want offline, but under certain assumptions, the payback and the break-even is the same, but it's not always the same. And this is why we are bringing it up here, because you really have to understand the differences here. And I don't go deeper into this, but we had discussions around this: why is break-even not payback, and how do you calculate it? I just want to point it out. Most of the time you will see in Xendee, it's very similar, but it can be very different depending on how the annual cash flow is. And I have a last slide here to show you this. And this is one analysis which shows completely different results on the break-even year and the payback year. And the rule of thumb here is, and this is just to memorize this, if the break-even year in Xendee is always the year where the cumulative cash flow turns green from the left, okay? And the payback year is actually when you go from the right, where it turns red again. And maybe, Ray, you want to explain why this is happening on a high level, and then we have maybe confused the people too much here, but maybe you want to say something about this.
Sure. So yeah, the advantage with payback here in general is that it can account for uneven cash flow. You may have some cost incurred in year 16, like a major overhaul for the generators or projected replacement for certain components. So you might get this overall negative cash flow for that particular year. And in this case, it's like negative $4,000.
Yeah. Okay. With this message, and also the message that it's probably important to settle on the metrics, and then maybe work with us to work on the specifics. I want to actually go to the last slide, and then we go into the model. So with energy as a service, which we are going to touch a little bit today, you can combine these different financial methodologies. And energy as a service basically just means it's a third party which installs the technologies, the generation technologies for someone else, and then basically provides the energy to that other company. And this energy as a service provider basically covers the investments, has to purchase additional energy if it's needed, and then creates a blended rate or whatever it is for their client and sells energy to this. And we have some methodologies in Xendee to actually calculate those blended rates if you're an energy as a service developer. Okay, so with this, the last slide is yesterday. More details can be found in our YouTube channel, but just don't hesitate. Just reach out to Rita or to someone else on the team, myself, for all these questions. I just wanted to get the message across today that the financial methodologies and indices is a really important driver and have to be considered very carefully. So with this, I hand it over to Rita. Thank you.
Great, thanks, Michael. Let me go ahead and switch my screens. Okay, great. So this second portion of the session will be what we're going to call kind of a live training / walkthrough. In case you missed it earlier or joined later, for the actual live training and the 2-week free trial license of the Xendee software, we've just gotten such overwhelming response and registration. So instead of giving you the 2-week access and resources right now, we're actually going to give you everything. So your trial login, all the recordings, as well as the projects that we've modeled throughout this week after the end of the Xendee University Week conference. So it'll likely be early next week. So if you haven't gotten anything in your inbox about your trial login, don't worry, we have not sent that out yet. So this part will be kind of a live walkthrough. And this is the same data center example project we worked on in these sessions this week. So Monday, in case you missed it, was just a fundamentals training on setting up kind of a simple example project. In this case, we worked on a data center in the Bay Area in California. Wednesday, yesterday, we turned it into a more complex multi-node model and actually assigned the respective loads as well as DERs to their actual locations. We also added transformers, cables, and cooling pipes to show how Xendee can handle power flow and account for losses. For this one, we are going to be focused a little bit more on the financing aspects of the model and show how your financing methodologies can, in fact, affect your optimized capacities as well as financial performance. But just to kind of get everybody on the same page first, we're first going to go through just very brief how I set up this model, and we'll touch a little bit more on, where and when the financials can really matter. All right, so just a quick overview of this model. I kind of zoomed out on the Xendee software, design software here, but you can kind of see this is a site that we've chosen, which is a data center. So you can kind of see the facility here. So for this example, we're assuming that we're currently operating on purchasing utility electricity, and we have an existing electric chiller, which is this guy right here. So when you have your Xendee model, as you can kind of see as you browse the overall layout, there are several things you'll have to define, because remember, Xendee is a techno-economic design tool. So not only do you have to define all of your DERs, your technological piece, you also have to define your financial part, or the economic piece. So let's just go down in order of how I usually do things. So the first thing you always have to have is the load. We won't go into too much about the options of building your load profile, but there are many different ways you can do this. You can enter your load, you can enter your own load shape if you have historical data, and you can also build using one of our tools if you don't have that data on hand. So this is our data center electricity load. So you can see right here a preview of the dispatch. So you can imagine that our load, which varies between 6 megawatts and about 14 megawatts, this is going to be a huge driver for our utility purchases. Cooling is going to have a very similar shape, but just in a lower scale. So this is going to be a very important piece of what actually determines our utility purchases, is of course how much our load is. So speaking of the load, how we determine the utility piece of your techno-economic analysis is, of course, by knowing your electricity tariff. And we do that here in this electricity tab here, which is also what we call like our tariff interface. With just about every input in Xendee, you always have the option of setting it up manually. If you have like a historical bill or contract, you can build out different seasons. You can build out different tiers depending on consumption levels. You can add different time of use periods, which is going to be very critical for time of use tariff structures. You can add real-time pricing data, so actual time interval data where your electricity pricing might change hour by hour for the whole year. You can define your time of use definitions because this is how Xendee will know what time periods to apply which rate. If you switch over to the demand charges tab, this is where you can kind of build out the same thing, but for demand charges. Fees, how much you're just paying to access the utility. And we also have a functionality for exports. So this is when you have excess solar generation or other electricity generation that you want to sell back to the utility for revenue. And all of this you can adjust on your own, but what most of us will take advantage of is what we call the Bankability API. Xendee is a third-party company, and they're responsible for maintaining North American tariffs. So if you're in North America, Xendee is actually going to be a really easy way to import your tariff. And Xendee will know which load-serving entity you are under based on your project location. So our project's in the Bay Area in Northern California, so that's why we have the options for these two. So that's what I did for this project actually, is I imported the specific tariff from Xendee, which as you can see, it is a time of use tariff where we have different energy charges for period 1, period 2, which we can call, on-peak or off-peak periods, as well as a demand charge for the on-peak period. So as you can imagine, knowing the tariff in conjunction with our load, this is also going to be a huge piece of how we identify savings methodologies, as well as calculating our cash flow. The next thing you'll see here is fuel. Now, this is really important if you have fuel-fired technologies, which in this case, I do. I have a CHP gas generator, and we'll go back to this in a little bit to see more specifics on this DER. But the fuel tab is where you would define your fuel prices. And in Xendee, we have different fuel options, natural gas, diesel, biogas, hydrogen. You can also define your own. So this is where the fuel piece of the financial equation is getting taken into consideration. So we have a few other tabs here, and I won't go into these in detail for now. The next one, actually, I'll come back to the financing one later because this is where we're going to be running our optimizations to start with. But we also have a tab for incentives, which you can also define under specific DERs, but this is where you have the option to model some extra revenue streams, such as demand response programs. This is actually could be a whole lesson itself because there's a whole lot of different demand response programs out there, but just know that it is possible, and it is one way you can kind of leverage your DERs for savings or as a value stack. You can apply different grant fundings. And then we also have some common incentives that are usually more applicable to the US. We also have a tab for market participation. So if you have, spinning reserve, non-spinning regulation, and this is applicable for the BESS. Okay, so by now you should have gotten a good understanding of just how many ways your financial inputs can drive your techno-economic performance in Xendee so far. So let's now go into each individual technologies and look at how they're So in this model, what I have is I'm going to propose new technologies to add to our data center, just for the sake of maybe speed to power or not having to buy all of your electricity from the utility. So let's go look at our solar first. And I'll just briefly go over what it means at the top when it says technology decision. So basically, every time you add a DER in Xendee, you always have to tell Xendee how you want to consider this specific DER, and that's what we're calling the technology decision. So the first one is consider, and this is when you want Xendee to first figure out for you if it's even a good idea to install the DER, and if so, how much. So this is a great option if you have no idea if installing solar is going to even be a good financial idea, and if so, how much capacity. Existing is when you have existing assets on site already. So for example, like my electric chiller that's already on site. This is where you tell Xendee, I already have that asset and we don't need to pay for the initial CapEx because it's already paid for. We would just need to pay for reinvestment if it comes to reinvesting. Existing and more is going to be the same as existing, but you're also telling Xendee that you are open to installing additional capacities if it's a good idea. Forced, this is where you're telling Xendee that I know for sure I want to install in this new DER. So for example, if you figured out that you really want this 1 megawatt battery, this is where you tell Xendee, just put the battery in there, even if it might not be a good idea. Forced and more is the same, but you're telling Xendee it can recommend additional capacity if it's going to be a good idea. Okay, now let's go down to the investment specifications, which is again going to be a really important driver of your techno-economic analysis. So for the PV, or basically for all the DERs, you always have to define the per unit or like per kilowatt install cost, which is how Xendee will know the CapEx for your DER. You have to tell Xendee the lifetime because as we learned in the slide deck earlier, your lifetime can, justify your DER's investments, and it will also come into play if you're playing around with different methodologies as well as project lengths. You can define variable maintenance costs, which is going to go into your yearly OPEX in the cash flow, as well as install fees. If you scroll down, you'll see an incentive section, and this is where you can include in incentives like ITC for renewables, MACRs, but you don't have to use the default values, as we know some of these might change depending on where you are, where your technology is. You also have the option to enable or disable technologies for electricity export. And remember, I pointed out earlier that in the tariff window, we have a tab for configuring export rates. So this would be how you use that rate for electricity export and getting that revenue. Now, I won't go into the technical specifications. Maybe if we have more time, we can come back later and show the different ones depending on what people want to see. But just know that for every DER, you also have to define its technical specifications, which will drive its performance, output, and behavior in the dispatch. So that's my solar. In this case, I'm going to let Xendee decide for me how much to install. And we'll see in a little bit as we actually do the different exercises with the different financing methods, how our optimized capacity will change. Okay, so the next DER I have is the BESS. Again, I'm going to let Xendee decide for me how much, if there any, install or capacity to install. Again, I have defined the CapEx as well as maintenance fees and lifetime for the BESS. For BESS, when we can come back to this if we have time, you'll see that its technical specifications are going to be very specific to a battery energy system. So your charging rates, efficiencies, state of charge constraints. And just pointing out that for BESS, you do have a toggle specifically for ancillary services, which as we've seen in the market participation tab earlier, that's where you can get revenue from participating in the market.
Rita, can you stay on this? So I just want to have a comment here. So click on battery, please.
Oh, yeah.
Yeah, battery. So yes, this is a financial modeling session, but we decided we also go through more details today through on the technologies, because we realized that everyone was here on Monday. So this is also why Rita takes more time to talk a little bit about the technology, and then later on you will see the results anyway on the financial methodologies. But I also want to point something out for technologies, and if you're a very sophisticated modeler here, we have a lot of details for technologies. Like one of them is the temperature derating curve for batteries, so you can actually model how the temperature will impact your performance. And we have similar stuff on the CHP side, which will have nonlinear efficiency curves and all that stuff. So we never talked about this. We talk about today a lot about financing, but there's a lot of details also on the engineering technology side. And this is one of these details that you could model on how the battery will perform with different ambient temperatures, for example. Thank you.
Okay, so let's review the rest of our DERs quickly. The next one I'm going to talk about is our gas generator. And in Xendee, there's actually multiple different types of generator you can model. You can also do diesel, linear generator, gas turbines. For this case, I am just using a gas generator. And I am also going to let Xendee decide how many generators to install, if any. So the generator I've installed, or I've defined my per unit costs, as well as all of the technical specifications. For this specific generator, I am enabling the combined heat and power toggle. So essentially, I'm going to utilize this as a cogeneration unit where it can generate both electricity, but you can also utilize the waste heat, either to meet your heating demand if you have one, or we can use this in conjunction with an absorption chiller and use that waste heat for cooling. So that's what I'm going to do in our little example here, is actually use this in conjunction with the absorption chiller. And this is going to be a really powerful driver for saving not only costs, but also on carbon emissions. And you'll see here on the right-hand side, this is where I'm defining my fuel type. And remember when we reviewed that fuel tab earlier, this is where it gets tied to a specific fuel type and then also its respective prices. And just pointing this out, the generator does have a temperature derating curve. So if you're a more advanced modeler, this is where you can also kind of specify that relationship. And this could also impact your fuel usage as well as economic performance. If, for example, your generator derates to a very low percentage when it gets like super hot outside or super cold outside. So that's my CHP, which I said I'm going to use in conjunction with the absorption chiller, and that's what this is. Not too many on the screen here, but I'm also just letting Xendee decide how much to install. And of course, we have our existing electric chiller, which is what's currently meeting our cooling demand. And as you can see here, this is where I have told Xendee that this is an existing asset, so we don't have to pay for the upfront CapEx, but only the reinvestment if it comes to that. And Xendee knows when to replace it because I have also specified its existing age and lifetime. Okay, so now that we have all of our DERs, electricity tariff, and load defined, at the minimum, this is where you can start running an optimization to get a result. But let's go look at our financing method first. And this is going to be where we're going to see a lot of differences in the results. And so this is a financing tab. And as we learned in the slide deck earlier, there's 3 main financing methodologies you can choose in Xendee. So let's go with upfront cash purchase first, which remember is just buying everything upfront. So there's a few things you have to define, including your cash flow discount rate. And remember, this is how we're going to be able to calculate that cumulative cost into a discounted rate and get your NPV as well as your payback / break-even year. You have to define your project length, and we'll also see in a little bit how changing the project length in relation with your DER lifetimes can also change the profitability of your project. But let's just leave this on a default for now. You can also specify your reinvestment strategy because remember, if one of your technologies is going to expire before the end of your project length, Xendee is going to have to replace it. You can do accrued or lump sum, and you can see in the chart below, which is also the screenshots that we saw in the presentation earlier, how Xendee will set money aside in an accrued case, or you're just going to pay for it as reinvestment comes. So let's do accrued. And we also have this new functionality. If you're a current Xendee user, you might not have noticed this yet. This is our salvage value functionality. So this means that the part of the assets, if they're still going to have remaining lifetime by the end of your project length, you're now going to get a salvage value at the end of your project length. So let's just turn this on to see, where exactly it shows up in the project. If you scroll down, you'll see we have additional options for our service agreements. So energy as a service or charging as a service. And for either of them, you can combine it with any of the 3 financing technology or methodologies above. But we'll come back to that in a little bit. So let's just run an upfront cash purchase run for now. So at the main menu at the top here, every time you want to run an analysis, we go to the optimize window. And we also just call every analysis in Xendee an optimization because that is what Xendee is doing. It's going to find the best solution for you based on your inputs as well as your goals. So let's run a upfront cash purchase financing method. You have to tell Xendee your optimization decision because that's how Xendee finds the best solution for you. For most people, the goal is going to be reducing cost or finding the cheapest solution, which is what I'm going to use now. But of course, if your goal is reducing emissions, you can change it to that instead. You can also apply extra requirements like resilience and redundancy. For the reference model, we are going to use Xendee computed. And what this means is that Xendee is also going to calculate your reference case based on your existing assets. So remember that my only existing asset right now is my existing electric chiller, as well as my utility connection. So that's my reference case. It's basically buying all my electricity from the utility. As you can imagine, that's going to be very expensive. So in turn, with my new proposed investment in mix of DERs, whatever Xendee defines as to be, we're going to be comparing that against our baseline of basically just buying from the utility. At the bottom here, you'll see some advanced analysis configurations. And we have more documentation as well as guides on these if you're interested in learning more about them. I think we will talk about multi-year a little bit at the end when we have time, but just know that we do have guidance on these if you want to learn more about them. So when we're ready, let's run the optimization. And now Xendee is going to take all of your inputs, run through all of the equations, and give you a result. For a simple project like this, it's usually going to take, maybe 30 seconds to a minute. But if your project is more complicated, like if you have a multi-node project, or if you're using one of our advanced configurations, or if you have like a lot of constraints, that's when the runtime can get longer. But while you're waiting for your optimization to run, you can actually just go and make changes and then run another optimization while the first one is running. And you can have up to 3 optimizations running at the same time. Okay, so my first result is finished. So let's take a look. So what I'm going to do now is we'll quickly go over this first report in detail. And then for the rest of the reports that we're going to see, we're just going to look at how the financing component will change specifically. So every time you pull up a report, it's going to look something like this. At the top, you'll see, of course, your project details. And you can see this is how many equations Xendee had to run through to get to our result. So just a little over 200,000.
Let me add something here, Rita, because if you maybe remember, and if you were in yesterday's session, it showed 2 million. So this tells you how the complexity goes up with the multi-node version, right? So, and this is why, as Rita points out, it can take a little bit longer to run multi-node. But still, in this simple setup, we have 250,000, I just call it combinations. And in the multi-node, it went to 2 million. And if you have a large multi-node, like I was presenting on Monday, I think in the first session with UC San Diego, you end up with 20 to 30 million different combinations and solutions probably. So that's why optimization is so important to solve such complex systems.
Yeah, exactly. Okay, so on the top left-hand side here, you're always going to see this like summary savings table. You'll see your reference case, which again, remember our reference case is just buying from the utility, powering our electricity and electric chiller that way. So this is our reference cost, and this is calculated based on the load you've given Xendee as well as the electricity tariff that you've defined. The investment scenario is what we are calling our new proposed scenario. So remember, I added all of these DERs to let Xendee define and solve for optimal new investment scenario. And as you can see here, the costs are significantly lower. And this is how much we're saving in terms of annual system costs. Same thing on the right-hand column here, except for annual CO2 emissions. So how we're going to do this is this mix of DERs. So this is what Xendee has basically solved for us to be the optimal mix of DERs to invest in. So we have a good number of solar, battery, gas generator, and then some complementing absorption chiller. But we'll come back to this specific component here, especially the solar, which is what I'm going to change, let Xendee kind of have the free rein on as we go through the different financing methods. And we're going to see how this optimized solar capacity will change. If you scroll down a little bit, you'll see kind of a summary financing metric overview table. It's going to have a lot of metrics like LCOE, OPEX savings, break-even, payback year, IRR, NPV, which is usually going to be pretty important for you to evaluate your project. Now, let's take a note of the break-even and payback year here. They both say year 5, which might not make sense right now, but we'll go look at it in the cash flow table in a little bit. If you scroll down, you'll see a bunch of tabs in the report, and I'm not going to go into detail on every single chart, but I highly recommend you to do that and fully explore the report on your own when you get your 2-week trial login and run some projects on your own, because it is really important for you to understand your report and understand your savings and dispatch behavior of your project. But the summary tab is just going to have some summary charts on like your exploited value streams and overall system costs. Financial data tab, this is going to be one of the really important ones, and we'll come back to this repeatedly as we run more optimizations with the different methods. But you'll first see a microgrid cost breakdown chart comparing before and after. You'll see an ROI chart as well as cash accrued. Below, you'll see the cash flow tables, which is going to be one of the really important things to always check through. You'll have two cash flows. So one is the cost and one is the savings. So let's take a look at the cost one first. So the cost table is going to show you basically by line item how much you're going to be paying to operate your microgrid year by year. So like here is going to be how much you're going to be paying for utility demand charges every year, how much you're paying for electricity charges every year, how much fuel you're paying, any contract costs, DER maintenance costs. In the CapEx section, you'll of course see the CapEx for your new DERs. But then you'll see some positive numbers, and this represents income. So in this case, my incentives are going to be revenue, so that's why they're positive. You'll see the replacement costs for your DERs if they will need to be replaced before the end of your project length. So my electric chiller as well as my BESS, they both have lifetimes shorter than the project length, so they'll need to be replaced. And then at the bottom, you'll see the calculations that we also saw in the PowerPoint earlier. So how we calculate net annual costs, non-discounted, discounted, and then that's how we get the cumulative costs, both non-discounted and discounted. If you switch over to the savings table, this is going to be different from the cost table because the costs are straightforward, right? You know, it's how much you're spending or how much you're getting. It's an absolute number. The savings table is going to be produced relative to your reference. So it has to be calculated to your reference that you define. In this case, our reference is buying from utility. But if you have no reference or if you have like a manual reference, which is one of the options in Xendee, your savings can then change depending on what you're calculating with respect to. So again, you're going to have the line item breakdowns. So this is saying that in terms of utility demand charges, I'm going to be saving this much every year. It's probably going to be through demand reduction as well as peak shaving, but we'll see that in a little bit. This is how much you're going to be saving in terms of utility energy charges. Again, probably just through pure reduction. But as you can see here, we're going to actually have a negative cost or negative savings for both fuel purchases and DER maintenance costs because we're now having to pay for fuel and having to pay to maintain more DERs. So that's why these are negative. CapEx is going to be negative. So same items, and then down below, when you sum everything up, this is where you're going to get your net present value at every year, as well as the cumulative cash flow, non-discounted and discounted. And remember when we were talking about payback and break even earlier in the rule of thumb, how you determine each, this is where you would do that. So the payback year is the last negative year. So if we go from the right-hand side to the last negative year, that's going to be this year, which is, let me line this up. It is going to be year 4. Now, remember our metric table actually said year 5, but that's probably because it's due to rounding, because the actual answer when you do the math is probably like year 4.6 or like 4.7, but then in the actual table it's going to round it up to the nearest number. And then the break-even year is your first positive year. So that is actually year 5, and it lines up here. Okay, the next tab is the utility data tab, which is again another one that's driven essentially by your tariff inputs as well as your load rates and all of your financing inputs. So this is going to be a simulated utility bill of your new investment scenario. And as you can see here, it'll kind of break it down by energy demand as well as fuel, and also compare it to your reference. So this is essentially saying that as far as the utility bill, we're going to be saving this much compared to the reference. The energy balance and technology investments tab will have some just useful pie charts for, energy and electricity balance, where you're getting your energy from, how much you're operating them. So these are some helpful charts for your report. The dispatch is where you can see exactly how your microgrid will be operating. And this is the controller or the logic that you can give to your controller. So let's just quickly take a look at how this new proposed system works. So in your dispatch, you can view by month, as well as a representative date type. So let's take a look at a typical January day. This black line through the middle is the load. Remember, we defined the load. And the dark blue bars here are the utility electricity purchases. So it looks like we're just going to be buying in the very early morning hours and the very late night, which is the off-peak hours. So we're basically avoiding the on-peak hours altogether. So that's both going to save us on-peak energy charges, as well as avoiding the on-peak demand charges. The solar is represented by the yellow, so that's why it only shows up in the daytime. The battery is these green bars right here, and a state of charge is reflected by this pink line. So as you can see here, for the battery, we're charging it up in the very early morning hours when utility is cheap, and then we're discharging when it's on peak hours. The light blue bars is our CHP generators, so just helping out with the on-site generation. We have a heating dispatch because we have waste heat from our CHP, but all of that is getting directly converted into cooling for our absorption chiller. So now you'll see in this optimized case, all of our cooling is actually coming from our absorption chiller, which is this light blue, and we're not actually using the electric chiller anymore. Operation summary tab, again, just has more charts on how much your DERs are operating, as well as your monthly emissions. Last one is the print report, which you can print this out into a PDF, and you can actually customize what charts you want or you don't want. Okay, so now that we've reviewed just the overall basis of what a techno-economic optimization looks like in Xendee, let's go check out the different financing methods and see how our mix of technologies, particularly solar, is going to change. Okay, so let's go back to our financing tab and check out loan purchase. So once you switch it to loan purchase, you'll see there's going to be more inputs pop up, specifically your low interest rate, your cash flow discount rate, how much you want to finance, project length, loan length, as well as a debt service coverage ratio. So let's set our low interest rate to like a aggressive 8%. We'll keep it at the same cash flow discount rate, and we'll keep let's say just finance 80%. We'll keep it at 20 years for both the project length and loan length. So as you can imagine already, I have a pretty high interest rate and a pretty long loan length. So let's see, it will actually be less ideal to install solar. So let's run another optimization, and I'm going to call it loan purchase, 8% interest, 20-year loan. So we'll just quickly run an optimization. While we're doing that, let's go ahead and just run like a different one. Let's change my loan length to, 10 years. So we're gonna pay back our money really quickly and see if this actually makes a difference. And to look at all of your results and where they live, you can actually see all of them on the results page at the top. You'll see I already have a bunch of results in here from previous runs, but this is where they all are. And you can see here in the analysis type, like what loan, or not what loan, what financing method you picked, as well as what objective to pick. You'll also get more labels if you run like an outage or like redundancy or time series. But regardless, I like to keep my titles pretty specific. Just know I know what I did. Okay, so let's take a look at our result for the loan purchase with an 8-year or 8% interest rate and 20-year loan. So our solar here.
Rita, before we go into the results, there's a question from Scott, which I think is very interesting, and we have never touched on this, and I think it really should be discussed. So the question is, with this sample, is there benefit to running this in a time series model? I don't know it is specifically to this model, but there's something which we have only brought up briefly when we showed you this average load profiles, right? So Xendee can do a time series optimization. We can go down as a Xendee design in this techno-economic part can do time series down to 50 minutes, but it can do way smaller time steps in the one line. But then there's also this possibility of these typical days. And so you have a peak day, you have a weekday, and you have a weekend day. And Rita was showing this, or she's showing it now. And there's actually a debate around this because some people prefer time series data and some people prefer this average profile. And it has to do with risk. If you go with a time series data, yes, you get very detailed results, but you're also risking that you're designing the system on something which might be an outlier. This is why maybe a multi-analysis is good, or maybe going with historic data, which is more an average profile, and doing a day type optimization, which takes out the peaks. So this actually depends really on the preference and what you have in mind. And when we do typically these analyses, we do both things. We do a day type analysis, and then we do a time series analysis to see what's going on here. So this is a very good question. And actually, a lot of people are fighting over what the right way to do is. But I think we should do both because if you have an outlier data, then it could be an issue. And I'm not sure if you participated in the DOE session earlier, but Greg Valerie was showing exactly that. There was one for 2020 and 21 where the prices went up because of the crisis in Europe, between Russia and Ukraine. So there's always a risk that you actually design on something which could be too volatile or not realistic. And this is why you have both ways of doing this, or you do a multi-analysis.
Yeah, exactly. And yeah, actually we have the time at the end, we can run a time series because time series might also be necessary if you have real-time pricing where the price of your electricity varies, literally every single discrete hour of the year. Okay, so let's go back to our results. And just to remind everyone, in our upfront cash purchase, our optimal solar capacity was 17.7 megawatts. And now let's go look at our result for our loan purchase, 8% interest rate and 20-year loan. So, and then we see here, now the optimized capacity is only 14.1 megawatts. And this is probably because the low interest rate is really high. We have a really long loan term. So solar itself is not going to be as profitable in this case. And then if you go to our cash flow table, remember the cash flow table is where we break down everything line item by item, you'll see now we now have payments for our CapEx for year 0 through 15. And then after year 15 is when it ends. And you can also see in year 0, the amount that you're paying for CapEx is a lot higher because remember, we're having a down payment and then the rest we're financing. So of course, this will change depending on your financing amount as well as interest rate and loan term. So now let's take a look at what happens if we change the loan term to be from 20 years to just 10 years. So a lot shorter of a payback. So now we're getting about 14.9 megawatts of solar, which is higher than when we had the longer loan term, but still less solar than just when we pay for it upfront in the cash purchase. So now let's go and explore amortized cost financing method. So this one, you only have to define the interest rate and reporting years. You can input a max payback period if you want that constraint, but it is not necessary. But notice that this says reporting years. It doesn't say project length because remember, amortized costs, we're actually assuming an indefinite operational period. And we're amortizing all of the technologies based on their respective lifetimes. So really, this reporting year is just to limit, how many years we're reporting in the report because you probably don't want to report in perpetuity forever. Okay, so let's take a look at what happens if, we set out 8% interest rate. Amortized 8% interest rate. And remember, amortized cost is driven by the technology's individual lifetimes. And I think someone did bring this up earlier in the question, where, you might want to set where like your longest DER lifetime is going to be an important driver, but it might not be in every case. But let's just see what happens if we actually change the solar's lifetime. Right now it's 30 years, so it has a pretty long lifetime and it has more time to pay itself back. But if we change it to like 15 years per se, that means the solar is going to have a lot less time to, make back its value. So let's run the same optimization, but we've changed the solar lifetime to 15 years. But just as a general reminder, we're going to give you all your logins next week. And when you get your login, I really encourage you to actually go play around this with yourself because, we've covered a lot of things over the past week, but really playing around with yourself in the model and modeling things that you're interested in is really going to be the best way to get to know the software and see what it can do for you. Okay, so amortized 8% interest rate is complete. So we are actually getting an even lower technology capacity. 8% interest rate is pretty aggressive. So then let's take a look at the result for when we change the solar lifetime to only 15 years versus 30. So this has given us a drastically lower amount because, again, the solar only has 15 years to pay itself back before it has to be replaced. So looking at all of this, we can kind of get an idea of how both of your financing methods, as well as its specific inputs, can really change, what's optimal for your project because, you might evaluate it in one way given like, one set of market conditions or like one set of, DER manufacturers or models, and you might get a baseline expectation of like a break-even year in their financial performance. But really, if you try out, different market conditions or financing methods, you might see that, what you thought was going to be financially attractive might not end up being that after all. Okay, so let's move on to talking about multi-year, because I know we have some questions about this, and I just also want to show what multi-year can do for you as far as financial analysis. So multi-year, which is this left tab right here, is one of our advanced analysis configurations. So in multi-year, you have the option to input what we call escalators. So for example, if you're anticipating solar or one of the DER costs to actually decrease in the future, you can input, like a negative escalator. If you're anticipating the utility costs to go up for, demand and energy charges, you can then also say like a 5% increase. But you can also do a custom option if you're, want to vary it year by year instead of assuming the same increase every year. You can apply degradation factors. So like if you expect your solar or generator performance to go down year by year, you can increase your OpEx costs, fuel prices. You can also increase your site demand, and this is good for analyzing load growth scenarios. So like if you're expecting your profile or demand profile to increase over the years, or you're expecting like more people to use electric vehicle chargers over the years, this is where you can do that. So a lot of options as far as anticipating forward changes. And once you do that, you would have to run a multi-year optimization in the advanced configurations. Now, remember earlier when we mentioned, or we had a question about, if time series would be a good option for this model, or like when to use time series. For these advanced analysis configurations, like time series, multi-year, or one of these, you can only enable one at a time. So you cannot run an optimization with both time series and multi-year, for example. And that's just because these advanced configurations, they really add a lot of complexity onto the model. So it would essentially make your runtime a lot longer if you try to use multiple.
Let me add something here, Rita. So it's possible, and we internally run them, but we haven't released it to the public. But I mean, if someone comes to us and says, well, I want to do this in this combination, we can do it. But we want to guide that process because it can be a lengthy process. If you do a time series optimization for 20 years, then you can imagine that this could take a long time. So this also has to do something with guiding our clients to get reasonable results. But it's from a technical perspective, it's feasible.
Yeah, it is feasible. But right now, for our regular customers, you can only pick one. And this is why we're also saying that, for the sake of getting like a full understanding of your site and your performance, you should, or you could run optimizations with time series enabled, with multi-year enabled, basically different scenario analysis so that you can kind of see the project performance from all angles. There is a question about where the site increase in demand and the progressive unit rollout would be set. And yeah, that is where you would set it in multi-year. Right now, I have my financing method set to amortize cost financing, which is a method you currently have to use to have a flexible investment schedule. So you'll see here, I now have an investment schedule that I can select or deselect. So, if I want more investments in like year 5, this is where I can enable investments in year 5. And Xendee will also tell me, when my equipment is going to expire. But yes, this is where you would kind of model progressive unit rollouts. Okay, maybe
a note why we do this with amortized, because if you want to set a investment schedule, then a net present value calculation, upfront cash purchase doesn't really make sense, because if you have an investment schedule, either you take multiple loans out of it, or you see this in different projects steps. And this is why we said the fairest comparison, the easiest one, is if you use this with an amortized one, because there's no upfront cash or loan involved. This is why Rita said, oh, we do this with amortized. You can do a multi-analysis with net present value, cash, and upfront, but then this reinvestment schedule doesn't mean anything, because you have a project length of 10 or 20 years. So why would you set the reinvestment schedule if you already say that the project is 20 years long, right? So this is a little bit why this is limited here. And you can do multi-analysis with upfront, but the investment schedule doesn't make sense, because, I mean, you do everything upfront. That's the term of the investment methodology. It's upfront. So right. So why would you change this? So there's a little bit of a change here.
Okay, we have quite a bit amount of time left. Michael, do you want to, maybe take questions, or if we want to ask?
We should show some results on the multi-year, how they look like, and probably you just use a different project so that we get an idea about the results. And then if there's still questions left, we can answer them. And otherwise, as I said yesterday, I mean, everyone will be happy if they get some break in this long week. So.
Yeah, let me go ahead and find a good multi-year project, because I have a lot of projects. Okay, this is still a very basic project, and actually doesn't show the progressive investment, but it will show degradation factor, as well as increase in fuel prices, and just also how the multi-year reporting will look like. So when you run a multi-year analysis, it's gonna first give you like a multi-year summary first, because your annual costs as well as emissions is gonna go up year by year. Well, depending on what you said, but in this case, my annual system costs are gonna increase due to increasing fuel prices, as well as emissions, because I have degradation in my generator. And for the multi-year reporting, to get to the regular reporting that we were seeing earlier, so like the full comprehensive report, you would have to click into every year, because what Xendee does is it's actually still going to optimize every single year's individual dispatch. So it's all going to change year by year, and you'll kind of get the full report still, but it's going to be for that specific year. And for multi-year, you'll also see some multi-year specific charts that show the yearly increase. So like here, you see I have increase in emissions, as well as OpEx. And for the financial data tab, you'll now see that in the cash flow, the numbers are going to change, because remember earlier when we were looking at the cash flow table, all the numbers, they were actually the same year to year, unless you had like a macro structure for 5-year tax rebates. But otherwise, all of the numbers were the same year to year. In multi-year, you'll see your costs change if you apply escalators to them. So here, my fuel purchase costs are increasing year to year because I've applied an escalator to fuel costs. You'll also see energy balance charts, and that's also going to change depending on, if you have degradation on your DERs. And you'll also see your capacity of your microgrid change if you actually have future investments. For this one, I have the same amount of generators, but if you have additional investments, this is where you'll see your electricity or thermal capacity increase. Okay, so that's just a very quick overview of multi-year, but we also have on-demand resources, as well as walkthrough tutorials on multi-year if you want to dig into this more in detail.
So, and I think I will leave it there because I think it's really a lot that people have to digest here this week. So, let's keep it open a couple of minutes for questions, and if no questions are coming up, then I think we will give everyone 25 minutes back and a longer break before we go in a controller session this afternoon. So,
Yeah.
thanks everyone. Thanks Rita, Ray, and the whole team for making this possible. This was our last session. As Rita said, next week you will get the credentials. And then, of course, don't be shy to reach out to us if you want to know more help. Thanks, everyone.
Thank you, everyone.